Like genuinely, my brain is practically bleeding from the absolute incompetence of modern game development. Every single day you log on to Twitter or Reddit and it is the exact same argument. Oh, my 8GB graphics card is obsolete. The new unoptimized Slopfest AAA game stutters because it needs 16GB of VRAM to render a puddle of mud. Oh, poor little AAA game studio. They just couldn't possibly optimize their draw calls. They couldn't possibly manage their texture streaming pools. No. They just brute force everything and pass the technical debt on to you, the consumer. Ah, you must buy the new hardware to play our vaporware, yes? It's grifting. Pure, unadulterated market manipulation. But Nvidia just dropped a bomb at GDC 2026. And I mean a literal bomb on the entire rasterization pipeline. They just bailed out the entire lazy development industry and at the same time completely revolutionized how we handle memory. If you care at all about hardware, about why your SSD is full, or why games run like absolute garbage, you need to see this. Let's look at the Introduction to Neural Rendering presentation.
So, welcome again, everybody, and thanks for joining us. I'm Shannon again, and me and my colleague Alexi are going to talk to you a little bit today about neural rendering. So before we dive in, I wanted to give you a quick look at what we'll be covering today. First, I'm going to talk about the shift to neural rendering, what it means to move from hand-coded equations to learned representations, and what it makes to make those things work in real time. Then we're going to go into 3 case studies. Alexi is going to walk you through neural texture compression and neural materials. And then after that, I'm going to come back and tell you a little bit about how Omniverse NuRec uses neural rendering for autonomous vehicle simulation. And then we're going to wrap up by connecting the dots. We'll look at how the same infrastructure can apply across these and other neural rendering approaches. So I want to set the stage by talking a little bit about what neural rendering really is and how you might see it show up in practice today. So neural techniques show up across the graphics world in several different patterns, and they're not mutually exclusive. You might do your rendering in the straightforward, traditional way with meshes and lighting and shading, etc., using your traditional pipeline, and then use ML on the result in order to provide a quality or style uplift. In the keynote on Monday, Jensen showed DLSS5, which is an example of this type of neural rendering. Or you might use ML inside your rendering pipeline. In this case, your pipeline is still there and still mostly the shape that you're used to, but your neural networks will run inside of it, evaluating materials, decoding textures, and computing shading results. Some of the case studies today fall into this part of the umbrella, this part of the spectrum. And the example here on the slide is rendering of neural materials. And then finally, you might take a mostly or fully generative approach, where instead of a traditional pipeline, you have either a very limited or reduced pipeline, and a neural network is responsible for generating some or all of the frame. None of these is more or less neural. They're all part of neural rendering. And you see some really interesting approaches when we combine these things. Now, real-time graphics has always been a discipline built on clever approximations. We don't simulate every photon. Instead, we've developed mathematical models to approximate the behavior of light, materials, and geometry well enough to fool the human eye. And we do it fast enough to hit 60 frames or even more per second. Now, the traditional approach in graphics is hand-coded logic for explicit math equations. When you want to know how light reflects off a surface, you'll reach for a BRDF. And if you need to compress a texture, you use BSC7 or maybe ASTC. A lot of difficult engineering has gone into these techniques, and we understand the trade-offs well. But there is an inherent limitation. The trade-offs here are rigid. If you want higher fidelity, you need more complex math with more parameters and more memory. At some point, you hit diminishing returns, or possibly you can't even model the thing that you're trying to render at all. Neural graphics, neural rendering, takes this and turns it around. Instead of asking, what equation do we need to model this behavior, we ask, what data do we want to learn from? And so we model this behavior with complex, or we can model a complex nonlinear phenomenon that you might not be able to do analytically. And the representational power is pretty impressive. But the shift in mindset is significant. So what exactly does it take to run these things in real time? Okay, we're moving towards learned representation, but putting ML inside the rendering pipeline itself means that there are additional practical constraints to consider, and the ones that matter to you are going to depend on your specific use case. Some use cases require inference at pixel rate. If your network is evaluating materials or decoding textures, it's running millions of times per frame. And at that scale, the network has to stay on chip. You can't afford memory round trips in between your layers. That means you need to use small, fused networks, tiny MLPs, shallow and cache-friendly, woven directly into your shader code. And to get real throughput on the matrix math, you need to use cooperative vector and cooperative matrix operations that engage the tensor cores. Now, not every use case hits this constraint, but when it applies, it dominates your design. And then another constraint that comes up broadly is that deployment lives in a different world than your actual rendering pipeline. Very often we're doing our training in a Python environment, but our rendering pipeline is set up in languages like C++. It's already there, and we need to be able to use the same code both in training and in deployment, because when you have to maintain two separate code bases, you face a gap. Hand porting introduces subtle differences that over time make maintenance very difficult. Slang is designed to address those constraints. It's a shading language designed for differentiable and neural graphics. The core capability is first-class automatic differentiation. You can mark a function differentiable, and the compiler will generate the backwards pass for you. You can also provide custom derivatives for operations where you need explicit control, things like numerical stability or opaque operations like texture sampling. And then SlangPy is our Python binding layer. If you load a Slang module from Python in SlangPy, you can call its functions and get gradients back into your training loop. So the same Slang source that runs in your PyTorch training pipeline can compile to your production target without hand porting or maintaining two separate implementations. Slang also brings modern language features like modules, generics, and interfaces to help manage the shader permutation problem. And even better, you get the performance that you need in real time because Slang can compile down to CUDA or to the graphics-specific shading languages like HLSL and GLSL, and provide direct access to those cooperative matrix and cooperative vector APIs. So there's a lot of tooling that can help you make the most of neural rendering, but how do you actually use it in an application, and what does it look like? For that, I'm going to turn you over to Alexei to take a look at neural texture compression.
Thank you, Shannon. So let's take a look into more details on first our application, neural texture compression. And first question is, what is neural texture compression, or NTC? It's a machine learning approach for storing textures more efficiently. Instead of storing every texel directly, NTC compresses the texture into compact learned latent features that capture its essential visual information. At runtime, a small neural network running on GPU reconstructs textile values from these features, computing them on demand instead of reading large textures from memory. So importantly, NTC is deterministic. It does not generate any new content. Given the same latent features and network weights, it always reconstructs the same texture. So why NTC? Why are we looking at NTC in the first place? First, it provides significantly higher compression ratios compared to traditional GPU formats like BCN, allowing us to store much more text information using less video memory. Second, it works very well with high channel count materials. Complex assets with many material properties or packed features channel can be compressed efficiently without splitting or simplifying the data. And finally, this leads to practical benefits: smaller disk footprints, faster downloads, and more compact texture storage overall. So in short, NTC delivers better compression, greater flexibility, and improved storage efficiency.
Okay, stop the video. Do you understand what he just said? Because I guarantee you 90% of the internet just heard AI and completely tuned out. This is not DLSS. DLSS is a Band-Aid. It takes the final rendered image and upscales it. What they are talking about here is ripping out the foundational guts of the rendering pipeline. For decades, we have used standard block compression formats, BC5, BC6, BC7. The GPU takes a 4x4 block of pixels, called texels, and physically unpacks them into the VRAM so you can see the texture on a wall. But textures are huge. That is why your Call of Duty install is 300 gigabytes. But neural texture compression, NTC, completely bypasses this. It doesn't store the picture anymore, guys. It stores the concept of the picture as mathematical latent features. And then a tiny micro neural network on the GPU just inners what the texture should look like on the fly. It is brilliant. You are no longer loading massive image files from your SSD into your VRAM. You are executing a deterministic mathematical equation that generates the exact same texture every single time. The implications for memory bandwidth are staggering.
So the core component of NTC is latent textures. Instead of storing traditional RGB texel, textures are encoded into latent feature maps that contains compact neural representation rather than final colors. Each texel stores a feature vector describing material structure and properties, capturing the essence of the texture instead of memorizing appearance. In runtime, neural decoder reconstructs the full resolution texture from these latent features, generating detail only when needed. By learning shared patterns and removing redundancy, latent textures achieve very high compression while maintaining visual fidelity. So our network has two main parts: a compact latent texture and neural decoder. Instead of storing a full resolution texture, we learn a much smaller latent representation, greatly reducing memory usage while preserving essential information. To reconstruct fine details, we apply positional encodings to the UV coordinates before feeding them to the decoder. This adds high-frequency spatial information, helping the network better capture subtle details and repeating patterns, resulting in sharper and more accurate texture reconstruction. Let's take a look how NTC training process works. We start by applying positional encoding to the texture UV coordinates, which help the MLP capture high-frequency details. Light encode is also provided to give the network additional flexibility for representing complex texture variations. The network output is then compared to the original texture, which serves as the ground truth. From the comparison, we compute a loss that measures the reconstruction error, And using these laws, gradients are calculated, and both the MLP weights and Latin code are updated iteratively. Over time, the neural shader converges and learns to accurately reproduce the original texture. So let's take a look at the example. So this scene is Tuscanville scene. And in this image, we see the final render produced using BCN compressed textures. The entire scene fits within approximately 6.5 gigabytes of VRAM. And now we're looking at the same scene rendered using NTC, but this time it consumes just 970 megabytes of VRAM. As you can see, there is no significant differences compared to the original image. The image quality remains consistent, while memory footprint is dramatically reduced. Let's compare BCN texture compression with neural texture compression using the same VRAM budget. In this image, this scene is rendered using BCN compression using total texture memory footprint of 970 megabytes. And now the same scene rendered using NTC with the same amount of VRAM. And now it's side-by-side comparison. Even under the same memory constraints, NTC preserves significantly more texture details and visual fidelity, while BCN introduced noticeable compression artifacts. This demonstrates how neural texture compression can achieve substantially higher quality at the same memory budget.
I'm sorry. 970 megabytes from 6.5 gigabytes down to under 1 gigabyte. We are back in the GTX 970 era, ladies and gentlemen. Do you comprehend the sheer scale of this VRAM saving? That is an 85% reduction in memory footprint with zero loss in visual fidelity. But wait, think bigger. What does this mean for the hardware market? Show the screenshot. Yes, the Kepler_L2 leak. According to the most reliable AMD and Sony leaker on the planet, the PlayStation 6 is going to ship with only a 1 terabyte SSD and no disk drive. Why? Because Sony is heavily banking on integrating this exact neural texture compression into their SDK. It's the end of physical media as we know it. People are crying, oh, 1 terabyte isn't enough for PS6. Guys, if NTC gives you a 7 times compression ratio, a 150 gigabyte bloated AA game suddenly becomes 21 gigabytes. You don't need a 4 terabyte drive anymore. Your download times shrink. Your patch sizes shrink. The entire bottleneck of moving assets from the solid-state drive to the graphics memory is practically vaporized. It's absolute chaos for the industry, and I love it.
So, neural texture compression provides several practical benefits. It significantly reduces disk footprint, which means smaller game installs, smaller patches. It's important because textures dominate modern game storage. It's also reduced download bandwidths and update times. In some scenarios, it can lower VRAM usage by storing compact latent representation and decoding textures on demand. Importantly, this technology is already available. So today, you can download Nvidia RTX Neural Texture Compression SDK using this link or QR code and try it out. So conceptually, neural compression also enables high detail materials within the same memory budget by trading compute for quality. And with perceptual loss function, we can achieve higher compression ratio while maintaining or improving perceived visual quality. So let's take a look at second application of neural rendering, neural materials. So real-world materials serve as a core inspiration for neural materials. Instead of inventing arbitrary representation, we learn how physical materials behave in reality, how they reflect light, scatter energy, and respond to different viewing directions. So modern techniques allow us to render very complex material with high visual fidelity. However, achieving that level of detail in real time remains a major challenge. So the reason for this is that we're dealing with deeply layered materials. These materials are built from complex shader graph with many interconnected nodes and dependencies. As a result, evaluating them efficiently becomes extremely challenging, especially when we try to render everything in real time. This highlights an open problem. We still don't know how to simplify this. So what are neural materials? Neural materials represent material appearance using learned neural features instead of traditional parameters like texture or analytic BRDF coefficients. Rather than storing separate channels such as albedo, roughness, and normals, these properties are compressed into compact latent feature vectors. A small neural network decodes this representation to produce material response for a given direction or shading context. This allows many materials attributes to be stored and streamed far more efficiently than with conventional texture-based approaches. The main advantage is much smaller memory footprint, enabling richer material appearance within the same VRAM and bandwidth budget. It's also important to note that neural materials remain in active research area at Nvidia and across the graphics community, with promising results but limited production deployment so far. So let's start with the question, what makes material realistic? When we look at a rendered object and think it looks real, it's rarely due to a single shading model. Realism comes from layering multiple material components, each capturing a different type of light interaction. One layer may represent a diffuse color, another glossy reflection, and another subtle surface effects like clear coat or micro roughness. Together, these responses create the appearance of realism. So rather than a single equation, it's better to think of material as a stack of light responses working together. Now let's take this material and examine its component in more details. So let's build this material progressively. We start with the basic based ceramic layer, which serves as a foundation for everything that follows. We incorporate a gold vapor deposition layer into the material model, enabling us to capture characteristic reflectance and spectral behavior of the thin metallic coatings. Next, we add the clear coat glaze, which gives it a richer, more polished appearance. And finally, we add a subtle layer of dust to help place the object into the real world. These extra details bring the perfect synthetic look and make the material feel physically grounded. At this stage, we're working with the reference texture that contain 19 different channels and capturing all the material properties we need. Now let's take a look at how we represent all of this using a neural network. So we need to train a Latin code that represents textures of the material. Instead of storing raw color maps or traditional material parameters, we compress the texture information into learned embeddings. These Latin textures act as a compact feature representation. They capture the essential appearance information in much more efficient form. Then we train decoder MLP that takes this Latin representation and reconstruct the final material properties. Conceptually, this is very similar to NTC network. We encode texture information into a compact Latin space and use a neural decoder to recover the details, shading parameters when needed. So the latent texture we can use can be very high resolution, even matching resolution of the original material textures. However, instead of optimizing latent values per pixel directly, we introduce an encoder MLP. This network takes material parameters and maps them into latent code. This avoids treating each pixel as an independent parameter, which would be memory heavy and poorly structured. Instead, the encoder learns a compact and meaningful latent representation of the material textures. Importantly, the encoder is only needed during training. Once latent texture is generated, the encoder can be discarded, keeping the runtime model lightweight. So during training, the system acts as an encoder-decoder model. Material properties are encoded into latent texture, and the decoder predicts the final BRDF values. The training loop itself remains unchanged. We simply insert this structure latent bottleneck. So let's take a look at the video. I hope it will start. Yeah. So this is a render result for our neural material. So it uses path tracing for rendering, and again, original material here that we model, it has 19 different channels for all material properties, and our neural representation uses just 8 channels. Channels can be at arbitrary resolution from 8 to 64 bits of resolution. So for performance, what we report here is the total render time for a full 1080p frame render. It is one sample per pixel measured in milliseconds. And as you can see, those speedups range from 1.4x to 7.7x in this particular setup, which is fairly substantial improvement, especially at full HD resolution. So why we have that speedup? Why neural materials are faster? Neural materials are faster because they change how surface appearance is evaluated. Instead of running complex Berdiev equations and multiple texture lookups, we use a small neural decoder that directly approximates the material response. This removes expensive analytic Berdiev computation and replaces many textures like albedo, normal, and roughness with a compact Latin texture, greatly reducing memory bandwidth. Finally, rather than evaluating material layers sequentially, the neural decoder produces the full material response in a single efficient pass. So overall, neural materials reduce math complexity, reduce memory traffic, and fuse layered shading into one streamlined computation, making them significantly faster. So neural materials are an emerging research direction aimed at bringing highly complex material to real-time rendering. Instead of storing materials in a large set of textures, they encode material behavior in a compact neural representation. This allows complex appearance and light interaction to be represented far more efficiently, reducing memory usage and bandwidth while preserving visual quality. So at Nvidia, this is an active research area exploring how neural representation could enable high-quality materials in future real-time graphics pipelines. So with that, I'll turn it over to Shannon.
Okay, take a breath. Now they are introducing neural materials. Up to 7.7 times faster rendering. This is where the grift is going to happen. Listen to me. I know how game directors think. I know how publishers operate. If you give a game developer 7 times more VRAM overhead, they are not going to give you a game that runs at 1,000 frames per second. Absolutely not. In Soviet game dev, we do not optimize. We just fill the empty space. They are going to use all that extra freed up memory to push path tracing and hyperdense geometry that you don't even need. They will pack in 8K resolution textures on a literal garbage can sitting in the dark corner of an alleyway that you will never look at. And why? Because the AI is handling the compression, so the devs don't have to do the hard manual labor of optimizing their texture pools anymore. Please, just let me have high frame rates. No. They will consume every single byte of that 85% savings to justify not doing their jobs properly. Yes, the tech is a miracle. It is an absolute engineering marvel by Nvidia. But the side effect? The side effect is it enables maximum laziness at the studio level. What a time to be alive.
Thanks, Alexei. So you've just seen how neural techniques can transform material and texture representation inside the graphics pipeline. Now I'm going to take a look with you at a very different application, one where neural rendering helps solve a problem in autonomous vehicle development. An autonomous vehicle needs a driving policy, a learned system that decides what the vehicle should do in any given situation. Training that policy usually uses reinforcement learning, where the system receives rewards for positive behaviors like maintaining optimal speed and following distance, while receiving penalties for negative outcomes such as collisions or lane departures. And that takes an enormous amount of training data. It's far more than you can practically collect in the real world. Now, unlike large language models, gathering training data for autonomous driving in the real world is prohibitively expensive and risky because vehicle failures carry significant real-world consequences. Now, to solve this, developers leverage simulation, but that introduces another problem. If the simulated sensor data doesn't look realistic enough, the policy encounters observations at deployment that it never saw in training, and it fails. This challenge is widely known as the sim-to-real gap. Now, Gaussian splats, a neural reconstruction technique, can close that gap. They let you take video or multi-view camera feeds and reconstruct the scene in 3D, so you can render it from any viewpoint. Because the reconstruction is learned from real captured data, it looks extremely high fidelity. And you get a quality that is very nearly indistinguishable from actual captured video. This allows for techniques, or this allows you to close the gap, and we call this the real-to-sim approach. So how does neural reconstruction work? The goal is straightforward. Given a set of images captured from different viewpoints, you build a 3D representation of the scene that lets you render it from any new viewpoint, including ones that you never photographed. 3D Gaussian particle fields can do this by representing the scene as a collection of particles, each one a small element that contributes to the final image. To train the representation, you optimize the particle properties so that when you render the particles from each of the original camera positions, the resulting image matches the ground truth, which is the photograph that you actually captured. The closer your match, the better the reconstruction and the more convincing that your novel views will be. The resulting scene is filled with lots of tiny, overlapping, semi-transparent 3D ellipsoid particles. Each particle has specific properties, position, scale, rotation, and opacity that are adjusted until the cloud of particles, when projected back to the original camera positions, look like your original image set. Now, those particle properties are view independent, but observed color varies with the viewing angle, like when a specular highlight makes something look like the color of the light source instead of its own material color. So each particle also needs a way to encode that view-dependent color. Now, what's shown here is probably the most common solution. It uses a Gaussian falloff for each particle, densest at the center and fading out smoothly, combined with spherical harmonics to capture that view-dependent color. Now, this representation is built offline, and once it's done, the representation is fixed, and you can render it from any viewpoint, including ones that were never in the original data. That is novel view synthesis. Now, the results can be incredibly high fidelity. What you see here is a 3D Gaussian field scene rendered with ray tracing to give you higher order effects like reflections and shadows and depth of field. And as you can see, you can smoothly navigate the environment. You're not limited to the original camera positions. So why is novel view synthesis so important for AVs? It's because the point of AV policy testing is that the vehicle needs to do something different than what was recorded. It has to change lanes or brake for a pedestrian or react to obstacles. If you could only replay the original camera path, you wouldn't actually be testing anything, you'd just be watching a recording. Now, novel view synthesis is what turns that reconstructed scene into a simulation environment. The AV can run its own policies and make its own decisions and see a plausible rendering of what those decisions would look like. Now, you can also modify the scene. If you notice that white car, it wasn't in the original recording. It was actually inserted after reconstruction. So you're not limited to testing against the traffic that just happened to be there. You can create scenarios that never occurred in the real world, and that's vital for testing with scenarios that might be dangerous to record. But there are some constraints that you can also see in this video. Near the recorded trajectory, the rendering holds up well. But the further that you get from the originally recorded path, the sparser the information that the Gaussians have to work with, and the artifacts that start to appear. You can actually see a little bit in this video if you notice on the sides of that bus and the FedEx truck that we passed. So in that video, you saw artifacts kind of starting to creep in at the edges, but here's what it looks like when the problem is more severe. This is a reconstruction rendered really far from the original camera path. You can think of a Gaussian field as kind of interpolating between observed viewpoints. So when there are big gaps in between your observations, or you're extrapolating beyond them, the geometry can't be reconstructed faithfully, so you get this blobby thing that you saw there. So to address that, we bring in the information that the reconstruction doesn't have. And this is where we start combining approaches from the 3 columns at the beginning. So NuRec's fixer is a neural network trained with semantic world knowledge. It takes these artifact-laden renderings as input, and then it produces cleaned up versions. The network understands the structure of real-world scenes and uses it to fill in where the Gaussians don't have enough data. Here's the before and after. Let me see if I can replay it. Yeah, I can. The difference is pretty dramatic. It can be applied at render time or during training to improve the actual reconstruction itself by giving it more views to learn from, or both, depending on your rendering performance and training time constraints. But there's another challenge for reconstructed scenes. When you're driving, you might only see other vehicles at a single oblique angle. If you think of a car ahead of you in the next lane over, you really only get a really constrained view of it, maybe the back and a bit of one side and absolutely none of the front. And if that's your training data, you have a problem. Because the Gaussians can only be placed where there are observations, so you end up with an object that's only been reconstructed from one angle. And when a new policy drives the AV past that object into the next lane, you're not just getting artifacts from sparse information, you're seeing geometry that we never reconstructed at all. So this is a real example. The back of that bus turns absolutely to mush as we drive past it, and then the rest of the bus is kind of non-existent. So to tackle this problem, we developed a neural asset harvester. That harvester identifies individual objects in the reconstructed scene and extracts them, and then uses a generative approach, similar in spirit to Fixer, to fill in everything that the camera never saw. So what you're seeing here are vehicles that were originally captured from just 1 or 2 viewpoints. Next to each one is the completed asset, a full 3D Gaussian representation that you can view from any direction. And here you can see them back in the scene, and you can probably tell I'm having fun with it because twirling vehicular ballet isn't something we really need to train the vehicle on, but that's the point. They're full 3D objects now, and you can stick them wherever you need and in whatever orientation your scene requires. Okay, so stepping back to connect everything that we just showed, Gaussian fields give you photorealistic reconstruction with great rendering performance, but our data comes from vehicles driving on real roads, which means that the capture paths are inherently constrained. So you don't get to set up a camera rig and photograph every angle like you might want. That means that some views and objects will always be underserved by the reconstruction alone. So we augment it with Fixer and Asset Harvester to bring learned world knowledge to fill in the gaps that the reconstruction can't. This hybrid, explicit Gaussian representation plus neural diffusion, is shaped by the constraints of AV simulation. A different use case with different capture conditions might make different choices, or hybridize differently, or not at all. Making these choices allowed us to achieve a combined quality and performance level that neither approach would have achieved alone. So what it takes to build systems like these, Gaussian splatting is optimization based. So you train the representation by back propagating through your actual renderer. And that requires differential code. And Slang provides autodiff out of the box, which frees engineers from manually writing backwards passes. You can mix automatic and custom backward passes if you need to handwrite the critical parts and let the compiler handle the rest. And then a pipeline like NuRec's is built from lots of small pieces, losses, kernels, rendering operations, and Slang lets you compose those in a single language and then do the dispatch efficiently. And NuRec benefits greatly from the bridge between training and deployment, because Slang connects our Slang code to Python and PyTorch, so the same source drives both the training loop and the production pipeline. It's the same kind of infrastructure that powers some of the neural shading that you saw earlier. The same tools applicable across domains. Now, I mentioned a couple times that automatic differentiation is what makes it easier to write differential code. But maybe you're undaunted. What's a little bit of differential calculus among friends? But let's take a look at what that means just for this one straightforward function call, which takes only 2 scalar inputs. It's really simple. Now let's look at the backward pass. It's all of this, just for one function. Maintaining it is harder than writing it, because every time the forward function changes, this has to change too. A mismatch would cause a silent bug that just corrupts your training, and that's what slang frees you from. You can just mark the function differentiable, and the compiler will generate all of this for you. And then the killer function for NuRec, and a lot of simulations where you need to do experimentation or are working with research, is the Python integration. What you see here is the entire source code for a bilateral image filter written in Slang and invoked from SlangPy. On the right is the entire Python file, which is just 15 lines, including spaces, which loads the Slang module, calls the function inside of it, and passes the data. And then SlangPy handles the bindings and the dispatch for you. And you might notice, if you look close, that the Slang function operates per pixel, and it's SlangPy that automatically maps it correctly across the entire image that you provide by automatically vectorizing it for you. So that's the full story. Neural techniques showing up across rendering in shading, reconstruction, and generative approaches, and they're increasingly being combined. Tools that make this work, differentiable code, Python integration, and efficient GPU execution are impactful across all of them, and they're available today. So wrapping up, I'm just going to point you at some resources to help you dive deeper. There are a bunch of sessions here at GTC covering 3D Gaussian splatting, world simulation, and AV training, all happening tomorrow, which I've outlined here, including a couple training labs, connect with the expert pod, and then both Asset Harvester and NuRec are going to be available soon at the links I posted. So please take a picture for later reference. And then on the in-pipeline side of things, we've got several libraries available and ready for you to use. The RTX Neural Texture Compression library that Alexi mentioned earlier is available on GitHub, as well as RTX Neural Shaders, which has the tools that you need for the broader neural inference inside the shader approach. And then Slang and SlangPy are active open source projects in their own right. And I've included links to absolutely all of that as QR codes, so take a look and try it out. Please explore what interests you most, and Alexi and I are happy to answer a question or two right now.
So what is the ultimate takeaway here? Let's be real for a second. Nvidia just solved the VRAM crisis, but they didn't do it out of the goodness of their hearts. Think about the business perspective. If NTC becomes the industry standard, and you only need 1 gigabyte to do the work of 6.5 gigabytes, what does that mean for the RTX 50 series and 60 series? It means they can keep selling you cards with 8 gigabytes or 12 gigabytes of VRAM for $600, and you can't even complain about it anymore. That's the sound of your bargaining power deflating, because they will just point to this presentation and say, well, you don't need 16 gigabytes of VRAM, just use neural texture compression. The entire hardware narrative is shifting. We are moving away from raw, brute force silicon specs and moving entirely into an AI-driven, neural rendered software ecosystem. If a game doesn't support NTC in 3 years, it will be considered broken legacy garbage. And honestly, I am here for it. Bring on the neural compression. Burn the old pipeline to the ground. Just don't let these developers use it as an excuse to ship 30 frame per second unoptimized slop. Who am I kidding? Of course they will. Bravo, Nvidia. You broke the internet again. I'm going to go lie down.